Jean-Pierre, can you also start recording? Okay. Okay, so welcome everybody to this last episode of the Café for this season. We will probably start again in fall. And our last speaker is going to be Mike Shulman, and the title of his talk is The Derivator of Setoids. And Mike, whenever you feel like, the stage is yours.
All right. Thank you very much. All right. So yeah, I'm kind of amused by the title of this talk because I never imagined putting these two words, derivator and setoid, together. So I kind of had to give a talk about it and maybe write a paper about it. So the reason that I'm interested in this and sort of came to the things that I'm going to tell you about is that I was interested. I was wondering about what homotopy theory looks like in constructive mathematics. So I'm gonna be a little bit vague about what I mean by constructive mathematics. You can think about something like the internal language of a topos, or something of that sort. A theory of sets. Constructively, but actually it turns out that it's even already interesting to ask this question in ZF set theory without the axiom of choice. That it's already an interesting and non-trivial question. So why might you be interested in this? Well, there are several reasons. Maybe you're a constructive mathematician and you are interested in doing some of the things that classical mathematicians can do with homotopy theory. Maybe you're interested in building models of homotopy type theory in a constructive meta-language. Maybe you're interested in doing mathematics relative to a base topos of sheaves, and you'd like to include some homotopy theory and talk about things like simplicial sheaves and so on. And so doing the homotopy theory internally in the internal language of the topos might be interesting. There are various reasons that this might be an interesting question. I'm not going to say really much more about any of those, but just sort of talk about this question itself. But there are actually two different sides of this question. So on the one hand, there's sort of the formal aspects of homotopy theory, and I'll say a little bit more later about what I mean by that. And then there's the question about how particular homotopy theories behave, and particularly the classical homotopy theory of what people call spaces is perhaps sort of the most basic or the most interesting one to ask about. So let me start by saying a little bit about the second question, and then that'll sort of lead us back into the first one. Right, so what is the homotopy theory of spaces? In classical mathematics, there are a lot of different presentations of this. There are topological spaces, which is sort of the original one, if we use them up to weak homotopy equivalence. And now and then there are simplicial sets and semi-simplicial sets and pre-sheaves on lots of other different things. You can even use small categories if you invert the equivalences under nerves, and all sorts of models like this are now known to present the same homotopy theory. These are often called spaces because of the original model was topological spaces, but nowadays it's often better to think about these as a model structure, as a homotopy theory of infinity groupoids. And constructively, the topological spaces are generally not quite as well behaved as sort of combinatorial things, because for this purpose, because they're sort of less flexible. So we're probably going to use more sort of combinatorial things to do it constructively. So recently, people have been actually trying to do this. There are at least two of these models, and maybe three or more now have constructive versions. So there's a bunch of people who have studied constructive simplicial sets of different kinds. Earlier in this year, in this seminar, we heard about effective confibrations, but there's also another version of constructive simplicial sets. And a bunch of people, some of whom are present today, have been working on these equivariant Cartesian cubical sets with the goal, again, of modeling homotopy type theory. And this is also known to now, there's a model structure which is classically equivalent to simplicial sets. But as far as I know, it's not yet known whether these constructive homotopy theories, which are classically equivalent to spaces, it's not known whether they are constructively equivalent to each other. So that raises the obvious question of, if they're not equivalent to each other, well, which one of them is correct? Or maybe they're all correct in different ways, or maybe they're all wrong. How do we answer a question like that, and what does it even mean? So this is the sort of question that I'm interested in right now. And one way the obvious way to answer that question requires some sort of, well, okay, sorry. So here's one possible proposed answer that involves giving a universal property to the homotopy theory of spaces, which is analogous to a universal property of the category of sets. So it's a fact which is true both constructively and classically that the category of sets is the free co-completion of a point. So that means that it's freely generated under colimits, small colimits by a single object, the terminal object. And so what that means is specifically is if I have any other co-complete category, then a particular object of that category determines a unique co-continuous functor sending that point to that object and extending co-continuously to every other set. So my proposal for a characterization or a test for what it means to be the homotopy theory of spaces constructively is that it should be the free co-completion of a point in the world of homotopy theories. And this is true, this is a true statement in classical mathematics. So it's sort of reasonable to hope that it might be true constructively, at least, for some notion of the homotopy theory of spaces. And it's really nice because it's a universal property. So I'm a category theorist, so I like universal properties, but it also has other advantages. It characterizes an object up to equivalence, just like any universal property. But it also doesn't tell you anything, it doesn't require a priori assuming that that thing exists in order to characterize it. So we can say, state this universal property, and then go ahead and try to construct things that might have this universal property. So I think this is kind of a nice proposal. Towards the end of the talk, maybe I'll say some things about why this is maybe not so nice of a proposal. We might want to try to fix it or improve it. But for now, let's sort of take this as our guiding principle that we'd like to be able to study, to take this, to have a homotopy theory of spaces with this property. But in order to make precise what that means, we need to know what we mean by a homotopy theory. And this sort of brings us back to the first question of what about the formal aspects of homotopy theory constructively. So what exactly is a homotopy theory? What do I mean by that? There are many different possible answers. Probably one of the more classical answers in classical mathematics is that a homotopy theory is presented by a Quillen model category. If you don't know what a model category is, that's fine. I'm not going to say any more about it than this slide. It's some sort of structure that you can put on a model, on a category like topological spaces or simplicial sets to make it into a homotopy theory. And these people who have been doing constructive homotopy theory have found that the basic parts of model category theory work constructively as long as you do everything in a specified way. There are more advanced parts of model category theory, though, like the small object argument and localizations and so on, that seem to depend on the axiom of choice in different ways. More worryingly, it's kind of difficult to formulate the universal property of a homotopy theory in the language of model categories. So model categories are pretty good for talking about universal properties of objects of some particular model category. But when you start talking about morphisms between homotopy theories, model categories are very rigid. This is one of the reasons that better models were introduced more recently that we'll get to later. Also, another reason that I like to avoid model categories for now is that we know classically that every homotopy theory that's sufficiently nice can be presented by some model category, but without knowing very much about constructive homotopy theory, maybe we shouldn't assume that that will necessarily be true constructively. Maybe it'll turn out to be true, but maybe it won't, and maybe we'll need some sort of more flexible notion of homotopy theory to capture all the examples that we want. So the more recent models of homotopy theory are called infinity one categories, or even just infinity categories sometimes. And again, if you don't know what these are, then that's okay. I'm not going to say very much about them. It's a higher category that has morphisms, has one morphisms and then two morphisms and three morphisms and so on all the way up, and they're all invertible above dimension one. So two morphisms are like homotopies, and three morphisms are homotopies between homotopies and so on. And this is in classical mathematics, this is I would say this is probably now the standard way to formulate by properties. Here I mean the universal properties of particular homotopy theories, or like the ones that we're proposing for the operator spaces. However, even in classical mathematics, we have lots of models for these. We have quasi-categories and simplicial categories and complete Siegel spaces and various other things. And we also have sort of abstract frameworks that like Real and Verity have proposed. But none of these models, as far as I know, has been developed constructively yet. Finding a notion of which of them is correct is probably going to be, I would expect, at least as hard as deciding which model for infinity group weights or spaces is correct. So I don't think this is a very promising way to formulate this universal property at the moment in constructive mathematics. So instead, I'm going to propose to use this other less well-known notion of homotopy theory, which is actually predates the notion of infinity category for quite a ways, which is called a derivator. The word derivator is due to Grothendieck. Very similar notions under different names were studied by Heller and Franke at about the same time. Nowadays, this is the most common word, and people sort of put these definitions together. I will define a derivator later on in the talk, so don't worry if you don't know what it means. But the basic idea is that it's like a quotient of a homotopy theory rather than a presentation of it. So in any homotopy theory, you can always consider the homotopy category, where your morphisms are homotopy classes of maps. That's just an ordinary category, but it's not rich enough to do very much with. So a derivator enhances that homotopy category with extra stuff, but it still remains at the quotient level. And the really nice thing about it, yes?
There is a question from the chat by Paul Taylor. It says, the word classical and constructive have various different meanings. Which of them do you intend?
Which of them did I intend when? Most of the time, I'm trying to use the word classical mainly to mean classical mathematics. So mathematics with excluded middle and choice. It's possible that I occasionally slipped up and used it to mean long ago homotopy theory. But long ago, homotopy theory was all done with the axiom of choice. So there's not a whole lot of ambiguity. Was there a particular thing I said that was confusing?
I cannot reply for
Yeah. Paul, do you want to speak up?
No, it says that it's fine. It's fine.
Okay. Okay. Right. Okay. So the other advantage of the derivators for this purpose is that it's a one categorical concept. It's built out of one categories and not any higher categorical structure really. And those are something that we understand fairly well in constructive mathematics. So it doesn't depend on knowing what an infinity category is. It doesn't depend on whether things can be presented with model categories. And here's a nice quote that I like from Szysinski, who said that derivators give us the language to characterize higher category theory using only usual category theory without any emphasis on any particular model, and in fact, without even assuming we know already any model of homotopy theory. So that's what we're going to do now. We're going to characterize what a homotopy theory of spaces might be like constructively without assuming yet that we know any. Right, so now I want to explain what a derivator is, but before I do that, I'm going to talk about a particular example of a derivator, and then that will help sort of motivate the abstract structure of a derivator. And this example is the derivator of setoids. So I'm going to switch gears very sort of radically here and go talk about something that seems very different. So we can sort of forget about homotopy theory for now, although it'll be there in the background. So there's a well-known notion of the exact completion of a category. So we're going to say a category is exact if it has finite limits, and every internal equivalence relation has a quotient of which it is the kernel. So that's of which it is the kernel means that if you sort of internally, if you take the quotient of an equivalence relation and you have two objects of the original set that get identified in the quotient, then they were already related by your equivalence relation. That's sort of what we expect, how we expect an equivalence relation to behave. And there's a forgetful functor from exact categories to categories with finite limits, and it has a left adjoint in the two categorical sense, which is called the free exact completion. And I'm going to write this as E sub x, although sometimes it's also written as E sub x/lex. to emphasize that you started from a lex category, left exact, meaning finite limits. And so that gives us this construction it has a universal property. Why might you be interested in this? Well, there are various different reasons, but one reason is that something like realizability toposes, for instance, are often obtained as exact completions of categories of assemblies. So that's an abstract characterization of the free exact completion, but it also has various different concrete descriptions. And here's a particular one of these concrete descriptions. So you might think, your first thought might be, well, I want to throw in quotients of equivalence relations. So let's just take the objects of the exact completion to be equivalence relations in the original category. And then they can sort of stand in for what their quotients ought to be. And that's a good idea, but it doesn't quite work, because if you do that, then you don't yet have an exact category, because not all the equivalence relations in the new category have quotients. All the ones from your old category had quotients, but then you need to sort of do another step. And so you can do it all in one step by looking at what are called pseudo-equivalence relations. This notion of pseudo has nothing to do with pseudo in higher category theory, but it's sort of standard. So this is a pseudo-equivalence relation. It's just like an equivalence relation, except it might not be a relation. So it might not be a monomorphism. We have a span. It's not necessarily monic. If it is monic, then it's an actual equivalence relation internal to E. But if it's not monic, then we can call it a pseudo-equivalence relation if it has the same structure that an equivalence relation would have. It has a reflexivity and a symmetry and a transitivity map which satisfy the right equations. But we don't demand any laws on these as if we would if it were, say, a groupoid or a category. It's like a groupoid without any axioms, a structure without any axioms. And if you do this in the category of set, then this is sometimes called a setoid, pseudo-equivalence relation in set. And these are sometimes used in constructive mathematics to formalize things with quotients if you start from a world that doesn't have quotients or doesn't have well-behaved quotients. So like if you're trying to formalize mathematics in, say, Coq without any quotients, then you might want to be able to construct quotients, and so then you sort of have to sort of build them freely and sort of build your structures on setoids rather than on sets. That's where that word comes from. So these pseudo-equivalence relations are the objects of the exact completion, EX. And then the morphisms are going to be maps that preserve this relation, as you would sort of expect. So it's a morphism between the object of the underlying sets, and sort of a morphism that shows that it respects this equivalence relation in an appropriate way. But this sort of morphism passes to the quotient, but there's some sort of redundancy here, because just to know that it passes to a quotient, it doesn't depend on what that morphism is between relations, right? So this is sort of this F1 sort of tells me that my morphism F preserves witnesses of relatedness, but I could sort of take, I don't care when I'm taking the quotient how many different witnesses of relatedness there are. So if different F1s for the same F could produce the same map on the quotient, and even different F0s could produce the same map on the quotient if they're related pointwise. So we say we compose an equivalence relation on these morphism representatives, I'm calling them, when we say that two of them are equivalent if there's this sort of thing which you can think of as kind of like a homotopy that assigns to every element of X0 a witness that F0 and G0 are related to each other pointwise. So we quotient by that relation, and that gives us the free exact completion, EX, and you can prove that this has this universal property, so it's a reasonable thing to do. And I want to remark at this point that I can do this to the category of sets. As I mentioned, the setoid is often called a pseudo-equivalence relation in the category of sets. I am assuming that the category of sets does have quotients at this point. I'm working in constructive mathematics with sets, not just with types or presets or anything like that. And in classical mathematics, the category of sets is equivalent to its own exact completion. So we're sort of adding new free equivalence relations to sets doesn't do anything. But that statement is actually equivalent to the axiom of choice. So in constructive mathematics, or even in CF without the axiom of choice, this category of setoids, the set X, is bigger than set. And so it's something sort of fundamental to the behavior of mathematics that maybe we ought to be interested in what it looks like. So let me tell you a little bit about the structure of this thing. So it's supposed to be an exact category. I'm not going to tell you everything about where it gets its structure, but in particular, it should have finite limits. In particular, it should have products. So what does the product look like? Well, it's very easy. You just take the product of the underlying sets and the product of the relations. So the things are related pairwise. Pairs are related if they're related pairwise. And if I want to show that this has the right universal property in EX, then suppose I have morphisms, say from Z to X and Z to Y. Then I'll choose representatives, F and G, and then I can apply the universal property of these products in my original category E to get a pairing map which represents a morphism from Z to the product in EX. Okay, so that's pretty straightforward, but I had to choose representatives for these morphisms. All right, and that's okay to choose two things. I know I can do that, but it doesn't generalize if I want to talk about infinite products, unless I have the axiom of choice. So there's a theorem that if E is complete and the axiom of choice holds, then EX is also complete. It has all small limits. But without the axiom of choice, we can't really we can't do something like this. This is, by the way, this is the external axiom of choice, not the sort of internal one to E, whatever that might mean. Although if E is the category of sets, then those are the same thing, so it doesn't matter. But this is a little bit frustrating because there are, I mean, we can do this at least constructively without the axiom of choice. There is a sort of a product-like operation on EX, because if I have a family of pseudo-equivalence relations, I can take something that feels like it ought to be their product by just taking the product of the underlying sets, the underlying objects of E. But it's not a product in the category EX. It has some sort of universal property relative to cones of morphism representatives rather than morphisms. If I sort of already have the choices made, then I don't have to use an axiom of choice, but I can't formulate that universal property inside of this category EX, so I need to do something else. So one way to do that is to work sort of throwing the setoids everywhere, and instead of working with a category, I can work with an E category, which is a category enriched over setoids, so it has Hom setoids instead of Hom sets. That's one thing you can do. A different thing you can do is extend it to a derivator, and that's what I'm going to describe. So what is this? So suppose I have a small category of any kind, then I can talk about diagrams of this shape in EX in the usual sense. So this would be a functor from A to EX. And if I have a functor from A to EX, then in particular, every morphism in A gets sent to an equivalence class. Right? It gets sent to a morphism in EX, which is an equivalence class of these representatives. But I can instead consider a different kind of diagram which sends every morphism in A to a chosen representative of a morphism in EX. And I'm going to call this a coherent diagram. So it assigns to every object of A pseudo-equivalence relation. And to every morphism of A, it assigns a chosen morphism representative. And then I also need this to be functorial, but at the level of the morphism representatives, I shouldn't expect it to be strictly functorial. I should expect it to be functorial up to chosen witnesses. So there should be some homotopy-like thing, like there is for the quotient of morphisms, which witnesses that this diagram is functorial. Okay, so that gives me a notion of coherent diagram where I've chosen representatives already for the morphisms. And I can do the same thing for natural transformations between diagrams of this sort. A morphism representative between diagrams consists of chosen representatives for the components of my natural transformation and specified witnesses that they're natural. And again, now these things are not sort of the right thing, but I can quotient them by an suitable equivalence relation as I did in defining EX itself. And this defines a category, which I'm going to write as EX of A, who's of coherent A-shaped diagrams in EX. The crucial difference again is that in this the category of ordinary diagrams, I have families of equivalence classes defining the natural transformations and the morphisms, whereas here, instead I have equivalence classes of families. So I don't have to apply the axiom of choice to pick a whole bunch of representatives. And now with this definition, I can prove that these product operations and more general limit operations do have a universal property. So a limit is a right adjoint to a constant functor. There's a constant diagram functor that takes an object of Ex and sends it to a constant coherent diagram in some appropriate sense. And this functor has a right adjoint constructively, which is given by, in the case of products, is given by this explicit construction of products. In other cases, I can do something a little bit fancier. And you can do something for colimits too. If E has appropriate enough structure, then there's also a left adjoint, which is like a colimit type operation. So this gives us a way to talk about what these sort of infinite quote unquote limits and colimits in Ex, how they behave constructively, even though they're not actual limits and colimits in this category without the axiom of choice. And
Mike,
this essentially, yes.
I have a question. When you write EXA, but you're using coherent diagrams, are you really working in EXA, or are you working in this category that has some explicit structure made and some choices of things made? I mean, there's this category of some kind of graphs with symmetry and reflexivity and so on, and you're really mapping into that, aren't you? And then
it's like EX, right? So the objects of EX are pseudo-equivalence relations with chosen reflexivity and symmetry and transitivity operations, but its morphisms are a quotient of the chosen morphism representatives. And the same is true of EX. So its objects are diagrams with chosen morphism representatives and witnesses of functoriality and so on, but its morphisms are equivalence classes of families of naturality components and witnesses.
Okay, got it, thanks.
Other questions? Right. So this structure here is what we're going to abstract out of from exact completion to define a derivator. So here's a definition of derivator. This is not quite the classical definition. It's slightly modified to make it sensible constructively. So I'm not going to use very much about the details of this, but let me go over it briefly. So I'm going to assume that I have some sort of universe level so that I can talk about the category of small categories and the category of large categories, which I'm going to write in uppercase. And then a derivator is a two-functor which from small categories to large categories. So you should think about A mapping to EX of A. Right, and when E, my category E could be large, for instance, set. I want to think about set X. So E is large, then EX of A is also large, but A is a small category. Making this a two-functor means that if I have a functor between small categories A to B, then I can take a coherent diagram on B and restrict it to get a coherent diagram on A along this functor from A to B, and just compose all of these operations with the map from A to B. That's not very hard, and it also acts on transformations. All right, so it's a two-functor and it has some extra structure. First, we ask that it takes finite coproducts to products. So something that means that D of a coproduct is equivalent to the product of all these categories here. In classical mathematics, we generally assume this for arbitrary small coproducts, but in constructive mathematics, we can't get that without the axiom of choice. So as weaken this to the finite case. Then we have the second axiom says that equivalences or isomorphisms in EX are detected pointwise. So this is sort of what you think about in an ordinary functor category. An isomorphism, a natural transformation is an isomorphism if it's an isomorphism component-wise. And this is what this is saying here. We're saying, so if I take the category, the discrete category and the objects of A, then I can have a coherent diagram on A and restrict it to A0. So that's just a family of objects. And then if my natural transformation is sort of object-wise an isomorphism or an equivalence, then it's already an equivalence. So this functor is conservative. That's what that means. It's isomorphism reflecting. In classical mathematics, again, this is usually stated instead by saying that the family of functors that restricts to D of 1 over all the objects of A are jointly conservative. But again, that requires making some choices. So constructively, it's better to work with all the objects at once in a discrete category. And then we have these sort of limit operations, right? So like here, I said that for EX, these constant diagram functors have a left and a right adjoint. Actually, you can prove more than that. You can prove this, that for any functor in cat, this functor here, so that's this here, U star, has a left adjoint and a right adjoint. So these are con extensions, the left con extension and the right con extension along this functor U in this world of coherent diagrams. And then this last axiom says that these con extensions are pointwise con extensions, that we can compute with them using comma categories in a Beck-Chevrolet condition. So again, the details of this are not important because I'm not actually going to give any proofs involving the notion of derivator, but I wanted to give you some idea of what this definition looks like and how it sort of represents these limit and co-limit operations in a formal way. So a derivator is a category. You can think about D of 1, which is sort of the underlying category of D. And then these sort of D of A's are sort of a structure of a notion of coherent A-shaped diagram in D, which has suitable notions of limit and co-limit and con extension. Maybe worth mentioning that these constructively, the fact that I have these sort of discrete things here, if I apply D to a discrete category, then what I get is I get a family of categories indexed by sets, and this is sort of what you might call what's called a set indexed category, or you can a fibration over set if you like to think of it that way. So a derivator is in particular a set indexed category, but it's also more than that. It's a cat indexed category with these sort of limit and co-limit operations. So some examples, I already mentioned, as hopefully we believe that this exact completion is a derivator as long as E is sufficiently complete and co-complete that we can do this. Then there's sort of the quote unquote trivial example where if I have a category that's complete and co-complete in the ordinary sense, then I can take these quote unquote coherent diagrams to just be the ordinary diagrams. And then I have ordinary con extensions, which make this into a derivator. And then in classical mathematics, where I have model categories or infinity one categories in the axiom of choice, then it's known that any complete and co-complete homotopy theory determines a derivator. So there are different ways to prove this depending on what you mean by homotopy theory. But you have a notion of homotopy coherent diagram, and you can take the homotopy category of that to get a category M of A, and that gives you a derivator. So this was sort of the original motivation for this definition. And so now I want to use derivators to formulate the universal property that this homotopy theory of spaces ought to have. And so we need a notion of morphism between derivators. Since a derivator is a particular kind of functor, right? So D1 and D2 are two functors from cat op to big cat. So a morphism of functors is a natural transformation. These are sort of two categorical things. So a morphism is a pseudo-natural transformation. And then in this universal property of the co-completion of a point, we want to talk about co-continuous morphisms. Right? So an ordinary functor is co-continuous if it preserves co-limits in the sense that there's a canonical map that's an isomorphism. And there's an analogous canonical map, which is given by taking mates of something or other like that for any functor. If I have a morphism of derivators, then I get a comparison map between these left con extension operations and the operation, this morphism G. And I'll say that G is co-continuous if this is an isomorphism. And then I have a notion of transformation, which is a modification, this sort of two-dimensional thing in morphisms of two categories. And so then I get these Hom categories that define a two-category of derivators and a two-category of co-continuous derivators. So these are the co-continuous ones. And that lets us formulate this property, which is, as I said, is true in classical mathematics. So it's unfortunately a little bit hard to find this in the literature, the sort of different pieces of it in different places, but the basic theorems results are due to Heller and Szysinski, that the derivator of spaces, by which I mean like infinity groupoids, simplicial sets, whatever model we choose, is the free co-completion of a point in the world of derivators. So for any derivator D, then there's an equivalence of categories between D of 1, so this is the underlying category of D, and the category of co-continuous morphisms from spaces S to D. And that's an equivalence of categories given by evaluation at the terminal object of the terminal space. And you can enhance this to an equivalence of derivators if you like. This theorem is also true for infinity 1 categories, if you like, in classical mathematics, but this is the version that I'm going to care about for derivators. And the important thing about this is it's a 2-categorical universal property, by which I mean it's expressed by an equivalence of 1 categories. Right? So we don't need any higher categorical machinery, nothing of any higher categorical dimension than we needed for the same analogous fact about the 1 category set, which was also expressed by an equivalence of categories. The co-continuous functors from set to some other co-complete category are equivalent to that category itself, the chosen objects in that category. So it's a little more complicated than that because it involves these things of notions of derivator, but the categorical dimension has not gone up. So we can write it, we can ask it constructively. And this extra complication is needed because, as I said before, the homotopy category by itself doesn't have enough structure to even state what we mean by these homotopy coherent limits and colimits. So now at least we have a precise definition of this proposed characterization of the homotopy theory of spaces, that it should be the free co-completion of a point. I don't know whether such a thing exists constructively. I'm not going to try to guess whether constructive simplicial sets or effective simplicial sets or Cartesian cubical equivariant sets are a free co-completion of a point. But I think we should investigate that question. I think it is interesting. So for now, or for the rest of the talk, what I want to do is say something about what this S would be like if it existed by looking at some other derivators that ought to be localizations of it or subcategories of it that are sort of small and we can at least understand it in a more explicit way. Maybe I'll pause for questions.
Will you put the definition back up of the derivator?
Yes.
Is there a notion of a representable derivator homming into something gives a derivator? It smells like it.
That's this.
Okay. Yeah. Thank you.
Or generally for any category, I can hom into it and get a pre-derivator, which has these two properties. And then it has to be a co-complete and complete and co-complete category to get these two.
Maybe could you please say a word on why the theorem has something to do with co-completions?
Yeah. So let me. So if you're talking just about set, then the corresponding thing would be like saying equivalently that you have an adjunction of some kind from co-complete categories to arbitrary categories, and the left adjoint here maps the terminal category to set. Right? So co-complete co-continuous functors from set to some co-complete category C are equivalent to ordinary functors from the terminal category to C, which is the same as just C. Right? So this is the universal property of the category of sets expressed as an adjunction. So this means set is the free co-completion of a point. And so now we're saying something similar, where there's some kind of adjunction here, which sends the point to this derivator S of spaces. Does that help?
Yeah,
so
brilliant.
It's the free co-completion of a point in this sense. I mean, the analogy isn't perfect. I mean, you don't actually have a full adjunction here because of size questions and things like that. And sort of again down here, so this is, I should maybe put this in quotes. And there, maybe if you wanted to be really more precise about it, you should be talking about left derivators, which have only co-limits and not limits, because here I wasn't assuming that I had limits, here only the co-limits. But roughly speaking, this is the idea.
Thank you.
Oh, crap. Do this
again. And Mike, in your paper,
yes.
the universal property is phrased in terms of left derivators or derivators in general?
Well, I'm still working on the paper. At the moment, I've written it in terms of derivators, but it doesn't actually use any of the limits, so it might as well be left derivators. Sorry, I got myself completely lost. Okay, here we are. Other questions? All right, maybe I'll move on. So in classical mathematics, this derivator of spaces has a lot of interesting subcategories or subderivators or subhomotopy theories. Sets, for instance, are a subcategory of spaces, as you might call it the homotopy zero types, the discrete spaces. But you can also sort of go up in dimension. You can talk about the category of groupoids, which are equivalent to homotopy one types, which have no homotopy above dimension one. Sort of classically, these are the disjoint unions of Eilenberg-MacLane space KG1s. You can consider similarly homotopy n types, which have no homotopy above dimension n, which are sort of equivalent to n groupoids. And you can also go down one dimension and talk about the category of what constructively we like to call truth values. Classical mathematician would just say that it's either empty or contractible. And so this is sort of like the case n equals -1 or -1 types. And each of these examples that I've written here is also a free co-completion of a point in its own world, right? So set is the free co-completion of a point in the world of one categories, but groupoids is the category of groupoids is the free co-completion of a point in the world of 2,1 categories. So these are two categories where all the two cells are invertible. And similarly for n types in n+1,1 categories. And the category of a prop of truth values is in fact also a free co-completion of a point in the world of posets, which some people like to call 0,1 categories. So if we want to phrase a universal property like this in the world of derivators, to ask whether examples of this sort also exist constructively, we need a way to say in the language of derivators what it means to have a 2,1 category instead of an infinity,1 category. This is not as obvious as you might think, because a derivator, unlike an infinity,1 category, a derivator doesn't have explicit higher dimensional cells. Right, so I can say that an infinity,1 category is a 2,1 category if all of its 3 cells and higher are identities, for instance. But I can't do that in a derivator because I don't have cells up there. All I have are these homotopy limit and colimit functors. So instead, what I can do is I can detect whether a derivator sort of is 1 categorical or 2 categorical or whatever by looking at the behavior of limits and colimits of constant diagrams. So here's an example. If I have an object, then I can consider the equalizer of 2 copies of its identity morphism. And in a 1 category, this is just that object again. But in a higher category, if I take the analogous homotopy equalizer, or even just in, say, groupoids, I take the corresponding pseudo-equalizer, then what I get is a free loop space object of M. And so you can think about this in terms of universal property, like if I map into M, maybe I'll say it like this: if I have this equalizer and I map into it from a point, then what is that? Well, it's a point of M together with a homotopy or an isomorphism between the two composites over here in M. So it's a point of M together with a loop in M. So in a one category, the equalizer of this diagram is M again, but in a higher category, it's not. So that gives us a way to detect in terms of limits and colimits that we have in a derivator, whether or not the derivator is a one category in some sense. And the similar sort of thing happens one level down, which is maybe even more familiar. If I take the product of an object with itself, in a general one category, even that's not the object again, but it is in a poset. Meets and joins in a poset are idempotent. So that behavior, that sort of idempotence behavior of products allows me to detect whether a one category is a poset or not. Okay, so with that as motivation, we can write a general definition in a derivator that sort of allows us to detect this categorical level. This is a standard definition in the theory of derivators from classical mathematics. So what does it mean in a derivator to take the limit or colimit of a constant diagram? So I'm going to suppose I have some category A, and then I have the projection from A down to the terminal category. And the constant diagram on some object M is what I get by pulling back that diagram to A along this functor. And then the limit of that diagram is what I get by pushing it forward again along the right adjoint. So this here is the derivator version of the limit of a constant diagram over the category A. And I can define this notion more generally in a relative way by talking about a functor. I'm going to say that a functor is a D-equivalence if it induces an isomorphism between limits of constant diagrams. So the limit of a constant diagram on A is equivalent to the limit of the constant diagram on B for any object M. So for instance, this fact here in a one category is talking about the functor from the category that indexes equalizers to the terminal category. It's talking about whether or not this functor here is a D-equivalence. More generally, in a one category, regarded as a derivator, this constant diagram limit is just the power of an object by the set of connected components of the category. So this category here, for instance, is connected. So when I take the limit of a constant diagram, I just get that object again. I get the power by one object set, one element set. But if I have some other category that's disconnected, then I take the limit of a constant diagram. I'm just taking the product of one copy of that object on each component in a one category. And so that tells me that U is a D-equivalence if it induces an isomorphism on these sets of connected components. So in particular, this here is a D-equivalence for all one categories. And in fact, if D is set, then these are precisely the set equivalences. For another one category, there might be more of them, but for set, these are precisely the set equivalences. But for a general derivator, like spaces or groupoids, then there are going to be fewer D-equivalences because this map, for instance, will not be a D-equivalence in groupoids or spaces. In fact, the groupoid equivalences are the functors that induce an equivalence of the groupoid reflections. So capital Pi 1 here, I mean, I take a category and formally invert all of its morphisms to reflect it into the world in the category of groupoids. And so if U induces an equivalence of those, then it's an equivalent, it's a groupoid equivalence in the sense of the groupoid being a derivator. One level down, at the category of truth values, U is an equivalence for that derivator, a prop equivalence if it induces an isomorphism on pi minus 1, which another way, and pi minus 1 is just the assertion that the category is inhabited. And so U is a prop equivalence if whenever B is inhabited, A is also inhabited. Because of course, whenever A is inhabited, B is inhabited because we've got a functor. And in classical mathematics, the S equivalences for the derivator of spaces are the functors that induce a weak homotopy equivalence of nerves. And it turns out that this is sort of the smallest possible class of equivalences. This was the theorem, one of the theorems of Sosinsky, that the S equivalences, the weak homotopy equivalences of nerves, are the smallest basic localizer, which in particular means that the weak homotopy equivalences of nerves are actually D equivalences for every derivator D. And in particular for the category derivator spaces. And we have similar things for homotopy n types if we take the pi sub n of a category, or the n truncation of its nerve in classical mathematics. These two are true constructively. We can prove those constructively because we can build the derivator of from groupoids and from sets and from propositions as well, and characterize them in this way. Okay, so we have this notion of D equivalence that we can use to talk about derivators being sort of truncated or not. And now I want to use that to formulate a universal property for derivators like set or groupoid or propositions. So if I have two derivators D and T, I'm going to say that D is T local if every T equivalence is also a D equivalence. So remember, the set equivalences are the functors that induce an isomorphism of connected components. Those are also equivalences for every representable derivator, every complete and co-complete one category. So those are all set local. If I have a complete lattice, so it's a poset which is complete and co-complete, then it's prop local. And in classical mathematics, we can do something similar for all dimensions going up. So, and this gives us a way to isolate the worlds in which these subcategories of spaces ought to be free co-completions of a point. Remember, I said set is the free co-completion of a point among one categories. And in fact, it's also going to be the free co-completion of a point among one categorical derivators in this sense of being T local. So I'm going to say that T is a relative free co-completion of a point if it has this same property relative to T local derivators. So the ones where every T equivalence is also a D equivalence. So set, for instance, has a free co-completion of a point relative to one categories, which are all set local. And it also, in fact, it also has it relative to other set local derivators. And the same for prop and even for groupoids, we can prove that constructively. And in classical mathematics, this is true for other higher dimensions as well. However, something funny happens in constructive mathematics. So remember, we have this derivator of setoids, set X, which is sort of feels one categorical because we started from this one category, set X, and we sort of extended it to talk about coherent diagrams, but we quotiented all the morphisms, and we don't care about how many two cells there are between something. So it's one categorical in that sense, but it's not set local. The set X equivalences are the functors that induce an isomorphism of setoids of connected components. What is the setoid of connected components? So it's a pseudo-equivalence relation in set, where the underlying set of objects is that set is actually the set of objects of A, and then I take the quotient in the setoid way, right? So to get the set of connected components of a category, I quotient by the existence of some zigzag of morphisms in a category. So now I'll take the witnesses of equality to be the zigzags. That gives me a setoid of connected components. And this functor is a set X equivalence if it induces an isomorphism in set X between these setoids. And that's a stronger condition than being a set equivalence. And you can see that, in fact, the difference between set X equivalences and set equivalences is precisely the axiom of choice. So here's an example. If I have a surjection of sets, I can make it into a functor where the codomain is discrete and the domain makes it a fully faithful functor, and in fact, a weak equivalence of categories. And that's a set equivalence, but it's not a set X equivalence unless the surjection has a section. So if every set equivalence is a set X equivalence, then the axiom of choice holds. We can, however, prove that set X is also a relative free co-completion of a point relative to itself. And in particular, all these other exact completions are local for set X. So what does that tell us? that suggests that if there is a derivator of spaces in constructive mathematics that is the free co-completion of a point in an absolute sense, then the homotopy zero types in it must include not just the sets, but also the setoids. I don't have a formal proof of that, but what we've shown is that set X behaves like one of these sort of subcategories of spaces, like sets and groupoids and n types. It's a free co-completion of a point in its own world. And sort of if we have something which has this big universal property, then it should sort of include these sort of smaller worlds inside of it as well. So this is, on the one hand, this is encouraging because simplicial sets and cubical sets and so on kind of have this property. But it's also disturbing because maybe we want to use homotopy theory constructively to say something about sets. And so if we do, then we would have to pass back and forth between sets and setoids rather than actually having the sets sitting inside homotopy theory as the zero types, which is something that we care about and use in classical homotopy theory. This is related to the problem of defining realizability higher toposes, where the zero types end up being the sort of the realizability topos that you wanted it to be rather than some exact completion of that. It's not exactly the same, but it's related. Okay. How much more time do I have? Any?
So I would say you have 5 minutes, 7
5 minutes.
if
Okay.
you need.
Great. So let me sketch a little bit more about what this preorder of free co-completions of a point looks like, because I think it's really interesting. So we have the derivator set, and then we have prop and groupoids, and these are sort of bigger than each other in the sense that prop is set local and set is groupoid local, but not conversely. And then we also have set X, which and set is set X local, but set X is not set local. Set X is not even groupoid local. I can have a functor that induces an equivalence on pi1 without inducing an equivalence on these setoids of connected components, because the morphisms in pi1, this groupoid, are equivalence classes of zigzags. And so that having a map backwards on equivalence classes of zigzags doesn't immediately give me a map backwards on actual zigzags, which is what I would need in set X. Now, an interesting question to ask is, what are the subterminal objects in set X? All right, so set is the zero truncated objects in groupoid. Prop is the subterminal objects in set. So what are the subterminal objects in set X? And it turns out that those are the preorder reflection of set. So if I take the category of sets and I quotient it by identifying any two parallel morphisms, that actually gives me another derivator, which is also a free co-completion of a point. And it's bigger than prop constructively or without the axiom of choice. And it's incomparable to set, just the way set X is incomparable to groupoids. And neither of them is local for the other one. Now, you might wonder, is there something up here that sort of behaves like set, lives above set X and groupoid, the same way set X lives above set and set posts. And rather than ask that, I think I'm going to start by asking instead whether there's something in between set X and groupoids. It turns out that there's another category here, another derivator here, which actually sits between set X and set, which is the regular completion of set. So the objects of this regular completion are the actual equivalence relations, not the pseudo-equivalence relations, but the actual ones that are monic. That's also a derivator. It's also the free co-completion of a point, a relative free co-completion of a point, and its subterminal objects are also set posts. And it turns out that set reg is actually I think I said something false a minute ago. Set reg is actually the zero truncated objects in groupoids. It's not set. I think I misspoke a moment ago when I said that set is that. So if you think about that, what does it mean? An equivalence relation is a groupoid in which any two parallel morphisms are equal. Okay, so those are the -1 truncated, or so the zero truncated objects in groupoids. So yeah, in that sense, so now that suggests what is it that lives over set X and above groupoid here. So there's this much is conjecture. So I'm going to switch colors, but I think that what lives up here should be something that you might call R groupoids, which are groupoids enriched over equivalence relations. And then there ought to be something up here, E groupoids, that are groupoids equivalent enriched over setoids. And then sort of I would expect things to sort of continue on up in that direction, where you can have, say, two groupoids living over R groupoids, and then you would have two R groupoids and so on up like that. So what does this tell us? What does this suggest about homotopy theory of spaces? So all of these things, all of these guys are relative free co-completions of a point. So they should all sort of live inside the derivator of spaces. So I would expect that to sort of sit all the way up here in some sense. But this diagram also suggests that if we'd like to somehow get rid of the setoids, if we'd like to be able to express some kind of universal property or get some kind of homotopy theory of spaces where the zero truncated objects are actual sets, then maybe we should try to just sort of go up this column and see whether there's something up here that would be a better homotopy theory of spaces. And the guess for what that might be is the category of spaces with some kind of anafunctor between them. And down here, I might guess that there's some kind of groupoids with anafunctors between them, which might sit over set and under groupoid. So an anafunctor is sort of like a functor that's only defined up to isomorphism. Without the axiom of choice, I can't actually choose values for it. So this might be some sort of spaces with anafunctors. So I don't know whether these things exist, especially constructively without the axiom of choice, but I think it's an interesting question, whether we can find something like this, which would be more like sets and still be a homotopy theory. Maybe I'll stop there.
Okay, so thank you very much, Mike, for this talk and for closing with an open question, which is always very thrilling in a way. And I think now we can move to the question time. So if someone has questions, you can just unmute yourself and ask it.
Yeah, first of all, thank you for this talk. This was really interesting. I'm wondering, maybe you kind of explained this a little bit. So this is a bit of a vague question, but in this picture of these different, of this locality preorder, is there some, I don't know, pithy description of set X in relation to spaces in the sense of, like, you know, n types or spaces which only have structure up to n dimensions?
Yeah, I would expect set X to be the zero truncated objects in spaces.
In like a constructive sense?
In a constructive sense, yeah. So you would, so these guys here would be the zero types. And similarly, these would be the -1 types. If you can sort of see that happening in the existing models for homotopy theories of spaces. Like if you take simplicial sets, then a simplicial set has a set of zero simplices, it has a set of one simplices and sets of two simplices and so on. So if you require that to be zero truncated in the sense that, say, any two homotopies into it are homotopic and so on all the way up, then what you get is essentially a pseudo-equivalence relation, because the one simplices are your witnesses of equality, and you're considering any two of them to be the same up to some two simplex, but they're not literally equal. Does that help?
Yeah, that's exactly what I was looking for.
Great.
Do we know that we have this composite line from two groupoid to set X as well?
Well, I think it shouldn't be too hard to show that if you take the the short answer is no, I don't think so. I don't know if anyone. Well, I mean, okay. So you could. I don't think anyone has written down a definition of the derivator of two groupoids constructively. But you should be able to say, like, I mean, all the basic sort of higher category theory that's sort of explicit, like sort of bicategories and tricategories, is constructive because it's just algebraic. So you could say, like, take the tricategory of bicategories and sort of quotient it in some way, and then presumably you could find set X inside there as the zero truncated objects, but I haven't written that down.
Thank you.
But it is here's something that is true. That's easy to see. If you can regard a pseudo-equivalence relation as a bicategory by just saying you have objects and you have morphisms, and then any two morphisms are uniquely isomorphic as by a unique two cell, and that gives you a bicategory. We didn't require any axioms on the composition in a pseudo-equivalence relation, but that's okay. We don't need any axioms on the composition in a bicategory. They just have to be isomorphic. So we say everything is, all the morphisms are isomorphic. We get a bicategory. And in fact, a pseudo-equivalence relation is precisely a bicategory or a bigroupoid in which any two arrows are uniquely isomorphic to it. Any two parallel arrows are uniquely isomorphic.
Thank you.
Okay.
May I ask one aside question? I would like to ask you, what is your deep motivation to develop a constructive homotopy theory? Why being constructive?
Well, let me go back to this slide here that I didn't mention. So, I mean, I would prefer, personally, I like not doing any of this. I would prefer to work in a foundational system where spaces are fundamental objects, like homotopy type theory, without having to build them out of sets. Because for one thing, that I think that generally tends to work better in terms of model semantics in higher toposes, and I also find it a little bit cleaner. But I think it's interesting to figure out to what extent we can do things without doing that, whether we can start from sets. I think I don't know. I mean, probably part of my motivation is a way for doing this is a way to complain. Because the various people are doing this. They're building these constructive models of homotopy theory and homotopy type theory, and they feel I get kind of queasy about it because of this setoid issue. And so I kind of wanted a way to sort of make precise what my queasiness about it is, and sort of what it would have to look like in order to make me happier, or sort of why I would prefer to do something different, if that makes any sense.
Thank you.
If I may ask a question, can you go to the last slide? So here you wrote S Anna up there.
Mm-hmm.
Do you mean infinity groupoids? What do you mean there? Is it
Yeah,
spaces?
some kind of infinity groupoids with anafunctors between them, whatever that means. So you could imagine something like simplicial sets where the weak equivalences are the the weak equivalences that sort of induce isomorphisms on homotopy groups or something like that. So, right, constructively, or like Kahn complexes are some sort of infinity groupoid. In the existing constructive versions of Kahn complexes, the weak equivalences between them are homotopy equivalences that have a map backwards. But you can have sort of a in classical mathematics, if I have a weak equivalence of Kahn complexes that induces an isomorphism in all homotopy groups, then it is a homotopy equivalence. But that making a map backwards uses the axiom of choice. So if I sort of invert those weak equivalences of infinity groupoids, that would be some kind of infinity groupoids and anafunctors.
And would it make sense, or it's just very different to study algebraic Kahn complexes in the sense that, okay, Kahn complexes are an injective family in simplicial set, right? So you could apply the Borg construction and make it algebraic. So you add a witness of being injective, and then you get, let's call them just for today, algebraic Kahn complexes. Do you think this could be the right guy? Because in this way, I'm adding a witness of the simplex at each step.
So again, this is all conjectural, so the existing constructive homotopy theories of simplicial sets already use algebraic Kahn complexes because they're not explicit about it but all of their lifting properties are given by specified witnesses and choices. My feeling is that for something like S Anna, you would still want that algebraicity, because I want to think of these things as infinity groupoids, and an infinity groupoid has composition operations. And I feel like that should still be true constructively. So my feeling is that one wants to weaken the notion of equivalence, or sort of have the functors, but maybe not the operations on the Kahn complexes. But it would be interesting to study all sorts of variations.
Thank you.
May I ask a question?
Yes.
Hi, Mike.
Hi.
Where in this picture would you land with set XX?
Good question. I don't know how to make set XX into a derivator, because set X as a one category is not complete and co-complete. And when I made EX into a derivator, I needed E to be complete and co-complete as a one category. I also don't know if there's a way to exact complete a derivator. It's a good question. I always sort of, it's an interesting question because if you just look at one categories, you have set, and then you have set X, and then set XX, and set XXX, and that process never stabilizes unless you have the axiom of choice. Whereas this derivator perspective seems to say that set X is somehow privileged above the double and the triple exact completions in a way that I don't fully understand.
Maybe a related question, though not entirely sure on that. In this diagram here, where we have like at sort of the level, level 0, we have set post and prop, and then we have set X, set reg, and set. And then I guess depending where you start, we have at least 3, maybe 4 terms on the next row. Do we expect that as we go higher and higher up, there would be more levels between, say, N groupoid and En groupoid, the N truncation that you described earlier?
Are you talking about more levels up and down, or more levels left and right?
Left and right, like in the
Okay.
sense that we have different things between the constructive and the classical.
Until we bring in the anafunctors, I'm expecting we only have three different things at each level, because we're sort of saying what's happening is at the top level here. Right? So at groupoids, the top level of the groupoid, that the 2 cells can be a set or an equivalence relation or a setoid. And those are sort of the only choices there. And similarly, the top level of a two groupoid is the two cells. Sorry, did I say two cells for a groupoid? The top level, the one cells of a groupoid can be a set or an equivalence relation or a setoid. The two cells of a two groupoid can be a set or an equivalence relation or a setoid, or whatever. So I expect only 3 at each finite level, and then the difference kind of vanishes when we talk about all the way up here, because there's no top level to talk about. Sort of everything is pushed all the way up. But you can also think about what this, instead of having just 3 things, you can think about it as sort of stabilizing after 3 things. Because if you look at, say, the subterminal objects in set X are also set posts. So really the sort of set post is also here. And I would expect the subterminal objects in E groupoids to also be set X. And so similarly set posts and so on. So this is, it's kind of like the, I'm thinking about this, you know, you're familiar with the periodic table of n categories, where you sort of stabilize things in one direction and like increase the dimension in the other direction. I'm thinking about this as a third dimension to that, where you sort of go out in the exact completion direction and it stabilizes after a certain amount of time.
Yeah, that was kind of what I had in mind, because there at each level you have, you know, it takes longer to stabilize. So I guess maybe that means that, like, I guess at each level we're starting at the top dimension. And if we were to say, you know, make one dimension up also be somewhat, yeah, I guess, like, would there be a way of imposing a sort of setoid-like structure at a lower dimension, which would maybe propagate out to the higher ones?
Well, so if you're talking about, say, the objects of a groupoid, you already have a setoid-like structure, namely the morphisms of the groupoid. If you want to impose an additional notion of equality on the objects of a groupoid, then you get into the world of like strict categories or strict groupoids and complicated kinds of E things. I wouldn't expect you to get a very good homotopy theory from that, because your sort of the homotopy theory of a groupoid resides in the fact that objects are the same when they're isomorphic. So if you're adding something else, then it's really more like a 1 category rather than a 2 category.
And then if we were to introduce these anafunctor analogs, do we think it would just add one level to the right of each row, or that there might be some like different levels of ana?
Yeah, I have no idea whether there's anything here. I know what an anafunctor between groupoids is. If I wanted to, I could write down what an anafunctor between 2 groupoids is. I can guess at what an anafunctor between infinity groupoids is, but I have no idea whether there's a thing here, whether there's some sort of partly anafunctor between 2 groupoids that's like ana, maybe it's sort of be anafunctorial on the Hom groupoids, but strictly ordinarily functorial on the objects. I don't know, maybe. It's a good question.
Yeah, thanks. The analog with the stability picture is really compelling.
It's fun.
So I would also have a question on the rightmost column.
Mm-hmm.
And before talking about constructions, if we want to talk about universal properties, can we add a condition to the definition of derivator that like gives a descent property for quotients already, in the same way that you already built in the descent for finite coproducts? Or
yes,
you know,
yes. So I think I have thought about this, and I think there's a natural definition. You can say that a derivator D is maybe I'm going to call it an ana-derivator, maybe. If U star is an equivalence of categories for any weak equivalence of categories U. So weak equivalence of categories is fully faithful and essentially surjective. And of the derivators that I've written up here, only these two are antiderivators. So it's natural to guess that maybe this column is the antiderivators.
Okay, yeah, that's not the condition I expected, but it looks good, and that's interesting. I was hoping that you can somehow directly talk about have a descent condition for quotients of of equivalence relations, but the base category isn't set, but cat, so maybe that's
right. So that's a very interesting question, and it leads me into something else. Classically, the two category cat is exact in the two categorical sense. And so you're probably thinking about, you'd like to have some sort of descent property for its quotients.
Exactly.
Constructively, the two category cat is not exact in that same sense. In order to make it exact, you have to work with antifunctors between categories. So this definition is another way of saying this is that D can be, since cat with antifunctors is what you get by taking cat and inverting the weak equivalences. This is essentially saying that D can be considered to be defined on the two category of categories and antifunctors, because D inverts the weak equivalences of categories. And then I guess you could impose an additional descent condition if you want, but I would worry about those as being something that wouldn't be true homotopically. Because I guess you might hope for some sort of infinitary descent property, but that's a good question. I don't know.
Thank you.
Since that came up, maybe let me just say that these things in the middle here, in general, are not well behaved categorically. Right? So set and set X are both exact categories, but set reg is not. It's only regular. Similarly, groupoids is not an exact two category, and I wouldn't expect R groupoids to be, but E groupoids, and maybe this guy would be, and so on.
If I may make a small comment, I would like to say that, in my opinion, the notion of left derivator is really better, more suitable in this case, because I mean, in a sense, the fact that the set is complete is a serendipity. I mean, it is the free completion of the point, and then it happens to be complete, in a sense.
Yeah, that's absolutely true.
And so, it has finite limits though, because this is part of the axiom. I mean, this is something that we cannot avoid, but definitely even arbitrary products is something we cannot expect in constructive mathematics. And so I would go for left derivator, maybe with finite limits, or I don't know.
Yeah,
like
yeah, you're absolutely right. And all of these free co-completions of a point that set X, I mean, saying that something is a free co-completion of a point in the world of left derivators is a stronger statement because there are more of them, but that stronger statement is still true about all of these examples, so that they don't need the limits at all. And that's especially important, actually, when we start talking about things like this, because I don't know how to, I mean, the category of groupoids and antifunctors, I think it's much easier to construct colimits than limits there. For instance, the groupoids and antifunctors is not Cartesian closed unless you assume some weak form of the axiom of choice, like whisk or multiple choice or something like that, which is sort of arguably constructive, but it's still an extra assumption. But that might not, and I expect that would also be true for limits, but it might not be true for colimits. So, I mean, the main reason that I'm writing about derivators is that they're sort of a more familiar thing that more people have heard of. But you're absolutely right that it's sort of left derivators are maybe more correct.
So maybe a little one, which is possibly off topic. The universal property that you talked about, can you prove the existence of a universal object without constructing it? like by abstract categorical arguments?
Yeah, that's a good question. Possibly. I don't know whether you could do that constructively. In classical mathematics, I would expect you should be able to do some sort of free construction, like just like a because the derivators are like an algebraic structure of some kind. So you're a two-categorical algebraic structure. So if you can sort of build free something or others, show that they're monadic over two monadic over something or other or something like that, then you would hope that then you would get a free one automatically. But those sorts of constructions tend to involve transfinite constructions, maxims of choice sorts of things. So I don't know whether you can do that constructively unless you have some replacement for that, like higher inductive types or something, maybe.
Okay, thanks. I think I see Ivan has spotted you here in the chat.
Do we have other questions? Yeah, in the chat I was ranting about the small object argument. I see two problems there, that the small object argument is not constructive and that there are some size issues popping up everywhere. So in a sense, I see two problems to solve there.
There are constructive versions of the small object argument, more constructive ones that use weak choice axioms like whisk. But it's not clear to what extent they can be applied here. It's a good question.
Last call for questions. Okay, so if there isn't any, I would like to thank Mike for his talk, and I would like to thank everybody for the discussion that followed, which was very interesting, and again for all of you that decided to connect today. So thank you very much to everybody, and again, this was the last talk before before the beginning of the summer, and we will meet again. Probably in fall. We don't have a date yet. It's too early. So thank you for joining, and see you in fall.
Thank you very much. Bye-bye.
Thank you.
Mike, thank you for the talk. It was very interesting.
You're welcome. Thanks for the invitation. It was fun. Some good conversation there at the end. Got some good ideas.
Okay, I'm closing the call.